Hello. In last video we saw how an estimate of this type, together with boundedness of the right hand side by the maximal function, led us to prove the inclusion that classical W1P functions on Rn are in M1P, the Sobolev-Hajlasz class. In particular, we showed that this right-hand side is less than some function g, which is in LP and non-negative, and that gives us the Hajlasz gradient. So we follow today with the proof of this representation formula, the proof of this lemma. Notice that the corollary is an easy consequence simply by taking absolute value. Well, I must correct myself by saying that in the actual inequality that we needed in that proof, we applied it, we had such an inequality. So this was not on all of our n, but it was some constant integral over a ball and then the same values. So this is a bit different because the integration happens only over the ball and your functions are not compactly supported on Rn, but rather you just need a W1P function on just the ball. So this is different, but the ideas behind, the techniques behind proving this inequality are very similar to the ones that you're about to see. So I chose this one, which is a bit simpler to write down, but at the same time contains the main tools and tricks of how such equalities and inequalities are obtained. Okay, where should we begin? Well, we can go back to our calculus 1. So this is x sitting in Rn, and then we can take some direction. Okay, some direction e, and the length of e is equal to 1. So some unit vectors. So in other words, this belongs to the boundary of unit ball. Okay, so fix some unit vector. Then, okay, so restricted to this line, you have a C1 function. And when you go far, far away, say you go to this y here, the value of the function is 0 there because our function is compactly supported. So when in finite time, you will reach a place where y value is just 0. So this gives you negative this. And then this, in one-dimensional fundamental theorem of calculus, this gives you, this is just derivative of that function along the line from, well, if we apply the time, so if you write this as x plus t e, and t goes from 0 to infinity, or 0 to the point where you reach this y. So this would be 0 from a cutoff t where you reach y, but if you continue for the rest of that interval, you lose nothing because, or you add nothing because it's 0 from that point on. So this becomes 0 to infinity. And what is the derivative of this function? So this is just gradient, the directional derivative in direction of e, which is gradient u at the point x plus te dot e, and then dt. Okay, end of the story. So what we concluded is that for any fixed unit vector, you have this equality. Now we can integrate this over all such e. So boundary is 0, 1 of, so negative is outside, ux. And suppose we denote by this, the Hausdorff n-1 measure, which is we can also use the sigma manifold notation for the measure on the unit ball. So E. Then this becomes, first of all, this u of x is independent of E. So this is nothing but u of x times the volume of the unit ball, which we denoted by n minus 1. So the volume of unit ball in our n is a constant depending only on n. Okay, then this becomes boundary, again, unit ball, and then the interior integral, which is 0 to infinity, gradient of u, x plus te, dot e, dt, and then d sigma of E. So all very simple. So we have one equality holds for every E, so we integrate over E's and it still holds. Now here comes somewhere where I don't know how to really explain, but Fubini's theorem applies here and allows us to switch the integration order. So I intentionally use parentheses rather than just two integrals next to each other to emphasize. So you first do one integral and then the other one. So when you do this integral, you just get something here with dt, you get something in terms of just E, and that's why you do the d sigma E integral. Now this time around, you want to do integration first over the ball of this function. So gradient u x plus te dot E, then d sigma E. And once you do this integration, you get some quantity in terms of t. So at this point, t is fixed. And only then you do dt. So that's Fubini, just to switch the order of the integration. But then what you can do is, well, every time, so in the inside integral, these are vectors which are t distance away from x. So x is here, and te, as E changes, so these are at distance t. So the interior integral happens over these values which belong here. Well, rather you want to kind of, a different notation is that you fix x and you call these vectors from here to here as y vectors. So y changes over the boundary. So this will be 0 to infinity, so I don't want to change that part. Okay, and then I will do some changes in the inside. So I'm doing an integral over this. Okay, suppose this is the unit ball. I choose my e's from there, but these quantities, or rather te, just te part is some vector here. So this will be E, and this will be te. And as E changes on this boundary, unit boundary, then this quantity changes along here. And well, the only reason why I'm going to do the next change is just because it makes calculations work. So I can do this integral, instead of doing it on the unit ball, I can shift the integration. I can pull back the value. So I'm going to integrate. I have a function defined here, and I'm integrating. I can pull the values here, the same quantities, 1 for 1, and integrate over the larger ball. So I do integration over the ball of radius t of same values. So this will be gradient of u. This will be x plus y. And then E is none other than the y divided by t. That is the relationship between y and te. Okay, this is doing, so this is the dot product of these two. But we have to also care for the volume change in going from this space to this space. Suppose you had a constant function, say 10, integrating it over the unit ball, you can easily do it by integrating over the larger ball, but you have to then pay off for the change of volume, for the Jacobian of that change of variables. And that can be done because for the same corresponding area here, how much bigger is this corresponding area compared to that one? Well, this is a manifold of dimension n minus 1, and if we multiply by t, that we stretch the volume by t to n minus 1. Now we used to do it on the unit ball, now we're doing it on, suppose t is much larger than 1 in a much larger ball, so we have to, if we do d sigma of this y value, we will get the volume, surface volume of the ball of radius t, which could be much larger, and we have to compensate for that, so we divide by this much. In other words, this and this together is a scale invariant integration on a sphere. So if you put this t to n minus 1, this radius of the ball, then integration of anything on this, integration on any of these balls of the same pullback of same quantities will be the same thing, because we again compensate for that. Well, some multivariable calculus going on there, but well, the other way, the algebraic way of thinking about this is just apply a change of variable which takes e to y, which is just te, and the Jacobian of that change of variables is t to n minus 1. But thinking about just how volume, surface volume stretches is sufficient, I guess. Okay, now you have this t changing from 0 to infinity, and then integration over these balls of radius t, and that should be familiar to you. So, well, not here. So you have a fixed origin, you have radius t, and then you integrate over this, and then over the next ball, and so on. And that is nothing other than integrating some function over the polar coordinates. So by using polar coordinates, or rather the reverse of it, this is nothing other than integrating over Rn, that function. So, but what is that function? So this is gradient u, so one other thing I need to say here, that when you pick y from here, d sigma of y, t is nothing other than the length of y. So in the denominators, you have t, which is absolute value of y, to power n minus 1. And then you have gradient of u at x plus y, then dot y. And then this is now only dy. Right. So the polar integral was that you vary your t, and then your y values are on the boundary of ball of radius t. Okay, so that's the reverse polar coordinates. And note that everything so far is just equalities. We have no estimates, no loss of values anywhere. This is basically now the inequality, the equality we wanted to prove, because I claim that this is actually nothing other than Rn. Look, when y changes, this quantity covers everything in Rn. Remember, x is fixed. But this covers everything on our n. This covers everything on our n. This covers everything on our n. But the difference is that these are the y quantities here and here are just shifts of this one. So I can change notation to say z or something, but I don't have to. So I can just, if this is called y, then this becomes just that quantity minus x. So this becomes 1 minus x. So y becomes y minus x, which because of this symmetry I can just put this to power n, because n minus 1 and n added up there, dy. So this is equal just to this one because y changed, well, rather, yeah, y minus x or something like this. It's a linear, it's a shift, it's a rigid translation, so there is no Jacobian, it's 1. And yeah, I don't know how to explain, but these two integrals are exactly the same thing. It's just a change of names. Again, this variable and this variable cover all of our n, so do these, and the difference in them is a shift by negative x, which is true also for the ones in the next one. And this is exactly the lemma we wanted. Remember, there is a negative sign right here, which turns this y minus x into x minus y. And we end up with this one. So that y minus x becomes x minus y. And also there was this volume times ux, so you divide, and there you go. So that's the end of the proof of this one. So the real tool we needed was the right application of Fubini's theorem. So this first line is really just one-dimensional fundamental theorem of calculus. And then, because it's true for every e, we can integrate over unit ball. Fubini allows to switch order. And then here we need to know how to do polar coordinates to get to an integration over all of our n. And we end up with this. Again, the message, the claim is that despite its look, this right-hand side is really nice operator, and we know a good bunch of bounds, LP bounds on this. In future videos, we will actually show how this inequality or its cousin inequalities, where you have, say, ux minus u average over ball less than some constant, and then integration over ball of same object, which has a proof similar to what we did. So how this and this can lead to Sobolev and Poincare inequalities, even for the range p strictly bigger than n, where you get filter continuity. But I hope you enjoyed this, and if you want to see more videos of this nature, where we do calculations and get to see multivariable calculus in hard work, let me know. Have a good one, and see you in next video.